Alright everyone, so in this video we're going to be going over two different examples of how to create Taylor series expansions for different functions. And for this one we're looking at the function ln of x, and we're going to be centering it about a is equal to 1. Here I just have the Taylor series expansion equation, and yeah, let's just get right into this one. So probably the first thing that we want to do when we create these Taylor series expansions is attack this part right here, this f, the nth derivative at a. So we're just going to do that part. We're just going to start doing that part right now. So we have f of a, and in this case our function is just this ln of x, but this one is in terms of x. So when we replace x with a, we just get ln of a. And now we're just going to take the derivative with respect to a every time. So here we're going to take the first derivative, a, and the derivative of ln of a is just going to be 1 over a. And now we just keep doing the derivative, and we keep doing the derivative until eventually we find, or we notice a pattern every time we take the derivative. So when we take the second derivative at a, we're going to have negative 1 over a squared. Taking the derivative again, so the third derivative, this negative goes away. And so now we get 2 over a cubed, because 2 times 1 is just 2. Now when we do the fourth derivative at a, the negative comes back in. And now we have a 6. 3 times 2 is 6, and now we have a to the fourth. And now doing the derivative one more time, 5. I usually like to take the derivative 5 times and see if I notice like any patterns within them. I also like to, I don't want to go too far with it, just in case if I make any mistakes, so that way when I'm writing them, I don't have to like erase as much. So when we do the fifth derivative, we now have a 24 at the top, and we have an a to the fifth. Okay, so now we try creating an expression for this f and the nth derivative of our function at a. So f and a. So now we try creating the expression. However, notice how for when n is equal to 0, so this one is technically 0, this is ln of a. So pretty much what I'm trying to say is that for when n is greater than or equal to 1, we notice we have a noticeable pattern that we could create an expression for this part. But this one is not going to fit anywhere in our expression because that's just ln of a. It's kind of not in a fraction form as these are. So we're actually going to exclude the first term when n is equal to 0. And instead, when we create our series, we're just going to write that one out and create our new series centered at, or starting at n is equal to 1. So here, when n is greater than or equal to 1, and that's all of this, that's pretty much what we're doing here. So now, we're just gonna write out the pattern that we notice when n is greater than or equal to 1. So notice how it's an alternating series. We're starting at n is equal to 1. So negative 1. If we're starting at n is equal to 1, and notice how we want our first term to be positive. So we're going to have a negative 1 to the power of n minus 1. Because when n is equal to 1, we're going to get 1 minus 1, and that's 0. So our first term is going to be positive. So that takes care of the alternating positive and negative part. And now we have to deal with this 1, 1, 2, 6, and 24. And notice how every time we took the derivative, we just multiplied by this power right here. So here we have 1 times 2, that gave us this 2. And we have 3 times 2, that gives us this 6. 4 times 6, that gave us this 24. And ideally for the next term, if we took the sixth derivative, it's going to be 24 times 5. But that's pretty much, what we're pretty much doing there is a factorial. So here, starting at n is equal to 1, here where we have here what we would have up here would be a 0 factorial. For this part, when n is equal to 2, we have a 1 factorial. When n is equal to 3, then here we have a 2 factorial. When n is equal to 4, the 6 can be turned into 3 factorial. And when n is equal to 5, this 24 can turn into a 4 factorial. So now, when we, in this expression, what we could do is write out n minus 1 factorial. And you could check that for yourself. That follows through with all the terms on the top. So we're good on that part now. And now we just have this a part, or the denominator, which is quite easy. We just have a to the nth power. So now we have this expression for our Taylor series, but remember this would be starting when n is greater than or equal to 1. Okay, so now I just erased a couple things, cleaned up the board a little bit, and now we're going to start writing our series expansion. So remember that this is starting when n is equal to 1. So for our first term when n is equal to 0, we're just going to write that part out. So we have our function ln of x. So when we plug in 0 for this expression right here, remember we're going to have that ln of x at the top. So ln of x, or actually it would be ln of a, sorry, my bad. And then here we would have 0 factorial, which is just 1. Then we have this x minus a to the nth power, which would also be 1 when n is equal to 0. So we would be left with ln of a over 1. And that takes care of when n is equal to 0. So now we can write out the series starting and n is equal to 1. And now we just plug in this part here by the Taylor series equation right here. We could just plug in this part for right here. Then we get negative 1 to the n minus 1 times n minus 1 factorial. And we have the a to the n. Now we also have to write out the rest of the things. So we have an n factorial in the denominator, as well as this x minus a to the power of n. And now here what we could do is plug in 1 for all of our a's. And see how this first term, when we plug in a 1, we're going to get an ln of 1, and that pretty much gives us 0. So this part completely disappears. And then here we have a to the nth power. When we plug in 1, we're just always going to get 1 every time for every term of this series. So this part can also just go away. And here we have x minus a. We're just going to replace that a with a 1. Okay, we could also clean up a little bit. So for this n factorial part, we could take out an n. So we would have n times n minus 1 factorial, and see how these just cancel out. And now what we're left with, ln of x, is the series starting at n is equal to 1 to infinity. And now we just write out what is left. So here what we get is negative 1 to the power of n minus 1. Actually, I'm going to write this on the top. So negative 1 to the n minus 1. Here we just have an n. And now for this part, we have x minus 1 to the power of n. So this is our Taylor series expression for ln of x centered at a is equal to 1. So that takes care of this problem right there. This would be our solution. Okay, so here we're going to be doing the same thing, writing the Taylor series expression or expansion for sine of x, but it's going to be centered at pi over 6, and we're going to be doing the same approach as we did with the last problem. However, for this problem, we're gonna have to do something different to write the Taylor series expansion. So yeah, let's just get right into this one. So first thing that we're gonna do is again attack this part right here. So we're gonna have f of a. So that's just plugging in a for our normal function. So that's just gonna give us sine of a. And this time what we're gonna do is just plug in a directly into here. So when we do that, we get 1/2. Now we take the derivative. When we take the derivative, we just get cosine of a. And so plugging in pi over 6 onto here, we get square root of 3 over 2. We do the same thing again, taking the second derivative. So we get a. This is going to give us negative sine of a. And we're going to get negative 1/2. Doing it again, taking the fourth derivative, we get negative cosine of a. And this is going to give us negative square root of 3 over 2. And for this problem, I'm going to take it a bit more further. So this is going to be the fifth derivative, but I think I'm going to take it to the sixth derivative. So when we take the derivative, we're going to get sine of a. That returns us back to 1/2. And when we do the sixth derivative, so f of 6 of a, that gives us cosine of a. And so this returns us to the square root of 3 over 2. So you kind of see a recurring pattern. It alternates between 1/2 square root of 3 over 2, negative 1/2 negative square root of 3 over 2, and then it goes back to 1/2. So the reason why I'm writing extra terms is because we're going to be taking the different approach. Because as you can see from here, because we're alternating between sine and cosine, we're not able to find a simple expression for the nth derivative of our function. So what we're instead going to be doing is writing out the first few terms of our series and see what we could do from there and see how we could write a series expansion just from writing the first few terms. So what I'm actually going to be doing is representing the 1/2 terms with the color blue. So we have there as blue, and the square root of 3 over 2 terms with red. So that way we could just keep track. So that way we could just put them together when we write out our main series. So we have sine of x, and we're gonna start with n is equal to 0. So when n is equal to 0, we start off with a 1/2 term. So I'm just gonna write out 1/2. And so when n is equal to 0, we get 0 factorial at the bottom. Then we get x minus a to the 0th power. So this becomes our first term of our series. Going on to our next term, we get square root of 3 over 2. So plus square root of 3 over 2. And now since n is equal to 1, we're going to be left with 1 factorial. Then we get x minus a to the first power. Then we do the same thing for our next term. We get negative 1/2. So we have negative 1/2. And this is going to be 2 factorial. Then we have x minus a to the second power. So now when n is equal to 3, we get, when n is equal to 3, we get negative square root of 3 over 2. All right, so 0, 1, 2, 3. Okay, yeah, my bad, my mistake. I was just making sure, keeping track. So yeah, I just realized. So let me change that up a bit. That's probably why it was throwing me off. So 0, 1, 2, 3. This should be the third derivative. This is the fourth. This is the fifth. Sorry. That's my mistake. I thought it was like thought I kept track of it, but now since we're back on track, here for when n is equal to 3, we get 3 factorial. First I thought I was doing it to the 6th derivative, but I guess I'm still sticking with the 5th derivative. But x minus a, here we would have 3. So now we have n equals 0, 1, 2, 3. And now when n is equal to 4, we go back to the 1/2 term. So we get plus 1/2. And now here we're going to have 4 factorial. So x minus a to the 4th power. And now when n is equal to 5, we get plus square root of 3 over 2. And now in the denominator, we're going to have 5 factorial. And then we have x minus a to the 5th power. And now we keep going. The next term is going to be negative, and it keeps on going forever. So now, this is where we start writing our series representation. So notice how for when n is equal, for our first term, for our series expansion, when n is equal to 0, we can represent these two terms together. Same thing for the next one. We can represent this when n is equal to 1. We can represent these two when n is equal to 2. And it keeps on going. So, sine of x. This series representation is going to be kind of long. Actually, I'm going to write that a bit lower. But I'm going to make sure it still stays in frame. So sine of x. So now we have this series representation. Starting at infinity, n is equal to 0. So now these two terms right here are actually going to be when we start our series, when n is equal to 0. So with that in mind, what we're going to do is the first terms are always going to have this 1/2. So we're going to just include that 1/2. But notice how the blue terms are always alternating between positive, negative, and positive. So I'm going to have negative 1 to the power of n. And notice how the factorials are all evens. So here I'm going to have 2n factorial. And same thing with here, the powers are also all even. So now we have x minus a to the power of 2n. Now we focus on the red terms. So we have a plus, and now all the red terms are going to contain the square root of 3 over 2. So we're going to include that in our series, square root of 3 over 2. And same thing for these are also alternating between positive and negative. So starting positive, negative, positive, we're going to have negative 1 to the nth power. And now notice the factorials, they're all odd, starting from 1, going to 3, 5. So if we're starting at n is equal to 0, we're going to want 2n plus 1 factorial right there. And same thing for here, all the powers here are also odd. So that gives us x minus a to the power of 2n plus 1. And closing off our series, this ends up becoming our series representation for sine of x centered at pi over 6. So this is pretty much the other approach when we are unable to represent the nth derivative of our function as like a simple expression. So we just write out the first few terms and see if we notice any patterns within that. And so yeah, this just becomes our answer for this problem. And hopefully this video helped you guys out. And yeah, see you guys later.